Hey, let's get started here. My name is Doug Cluck, and welcome to the January version of the North Central Climate and Drought Summary and Outlook. Zach Hoylman is going to be our presenter today. He's out of Montana. He's the Assistant State Climatologist out there. And remember, if you have questions as we go through this, let's see, where's the Q&A? There it is. If you hit the three little dots at the bottom in the circle, you can hit the Q&A button and ask any question you want. We'll get to those later in the show, so to speak. So if you have any questions or comments, do them there. We tend not to monitor the chat as closely. And I think at that point, Zach, you can take it away. Thank you very much.
Fantastic. Thank you. And good afternoon, everyone, or good morning, depending on what coast you are on. I'm just going to check, make sure I can advance. Okay, fantastic. Thank you, Doug. I'm excited to be here today and to present the North Central U.S. Climate and Drought Summary and Outlook. Again, my name is Zach Hoylman, and I'm the Assistant State Climatologist for Montana and a Research Assistant Professor at the University of Montana. 2025 as a whole and the start of the 2025-26 winter was one for the record books, with extremely warm conditions across the western portions of the region, a generally unconventional snow season, a record dry conditions in parts of the upper Missouri River Basin, and much more. Furthermore, a wild wind event caused significant impacts across the region. These conditions have contributed to some areas of significant drought, especially in places like Indiana, Illinois, Colorado, and elsewhere. We're going to be talking about all of this and more today. There's a lot to cover today, but before I get started, I want to mention that my presentation draws from information, data, analysis, and many helpful discussions across state and federal partners. Specifically, regional climate services for the North Central United States are provided by state climatologists and the American Association of State Climatologists, as well as state climate offices, the National Oceanic and Atmospheric Administration, or NOAA, the U.S. Department of Agriculture, USDA, Midwest and High Plains Regional Climate Centers, as well as the National Drought Mitigation Center. And just so you don't miss it, the next webinar will be on February 19th, 2026 at 1 p.m. Central, or if you're like me, 12 p.m. Mountain. And the presenter will be Austin Pearson from the Indiana State Climate Office. You can access future climate webinars and information at the link listed here. And finally, you can find recordings of past webinars via the Regional Climate Center links that are shown below. My presentation today will start with a recap of 2025 climate, then focus on how these conditions that we've experienced over the last couple of months compare to historical conditions, an evaluation of current snowpack and lake ice, hydrological conditions across what we call the critical zone, how these conditions have resulted in improvements and degradations in drought, a discussion of some impacts from these recent events, and conclude with a series of near future climate and drought outlooks. I'm going to attempt to complete all of this in the next 40 minutes or so, and then we'll wrap up, like Doug said, with time for questions and hopefully some further discussion. So now that we're a few weeks into 2026, we have a complete picture of 2025. So I thought I'd begin today's presentation by taking a step back and taking a look at 2025 and how it compared to the period of record going back to about 1895. 2025 was one for the record books. Let's dive in now and see how it compared to the last 131 years. The rankings that I'm showing you on this slide are from NOAA's National Center for Environmental Information, or NCEI, and compare 2025 average temperature on the left and precipitation on the right to those that have occurred over the last 131 years. Larger numbers, up to 131, indicate very warm conditions in red on the left, or very wet conditions in green on the right. Smaller numbers, down to 1, indicate increasingly cooler temperatures in blue on the left, or very dry conditions on the right in brown. As you can see on the left, there's not a whole lot of blue on that map, which shows that the temperature rankings across the domain have been quite hot. In fact, all the states in the dark red colors had the hottest year on record. All the states in salmon colors were very close to their hottest year on record, generally about 1 to 3 years that were warmer. Overall, 2025 was the fifth hottest year on record when accounting for the entire United States. As you can see, the Western U.S. was especially hot this year, with record heat in places like Nevada and Utah. Precipitation, on the other hand, was more moderate. On the right, I'm showing the 2025 precipitation ranks. As you can see, a few states did have wetter than normal years, including places like the Dakotas, Kansas, Oklahoma, and Kentucky. However, the majority of the central region where we're focusing today had normal to below normal precipitation. Very quickly, globally, 2025 was the third hottest year on record, with near record low sea ice and snow cover. Altogether, 2025 highlighted a warming world marked by widespread heat and only moderate precipitation at the annual scale. Okay, now let's look at more recent conditions. In this slide, we're going to take a more seasonal look at temperature and precipitation rankings, driven by the last 3 months. Again, these numbers are derived from NOAA's NCEI and follow the same color scaling as before. However, these maps compare October through December average temperature and precipitation to those that occurred over the last 131 years. The figure on the left once again shows statewide temperature ranks. The majority of the country, especially in the West, experienced a very warm fall and early winter. In fact, almost the entire Western United States had the warmest October, November, and December on record, as seen by every state with that dark red coloring. Furthermore, temperatures became less extreme the farther east you go. As you will see later in my presentation, these warm conditions have created an odd or generally non-existent snowpack across much of the West. When considering the entire country, October through December was the fifth warmest on record. Moving to the right, the 3 month precipitation rankings show a different pattern. It has actually been relatively wet over the last 3 months in the upper portions of the central region, particularly in states like Montana and North Dakota, where December was especially important for pushing these rankings even higher, which we'll look at soon. However, the middle and lower portions of the Missouri River Basin had a drier than normal 3 months. While the upper Missouri River Basin tended to trend wetter, drier conditions at low elevations and downstream may complicate basin-wide runoff timing and management. We'll take a look at that later on. Taking a slightly deeper look at the data shows some interesting patterns that are lost when you aggregate to the state level. Here I'm showing the underlying data that generated the previous graphics. On the left is the temperature percentiles presented in the same fashion as before. On the right, I'm showing the absolute departure from average, which gives you a sense of how warm it actually was. As you can see, large portions of Nebraska, Kansas, Colorado, and Wyoming had their warmest October through December on record, which was 4 to 8 degrees Fahrenheit warmer than normal over the last 3 months. That's very significant for such a long period. Okay, now let's move on to the last month's ranking. Here, I've shown the same maps as in the last slide, but with temperature and precipitation rankings for December only, so a 1 month period instead of a 3 month period. Patterns of temperature in December were generally similar to those between October and December. Hot, 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 especially in the West. In fact, every Western state except for Idaho and Montana had their hottest on record, with Idaho only having one December hotter than 2025. December was the fifth hottest December on record for the country as a whole. And in general, there was a progression from hotter conditions in the western portions of the central region compared to the east, as you can see. Moving on to precipitation on the right, we can see some recent dryness across Nebraska, Kansas, Missouri, and Arkansas, with Oklahoma having its driest December on record. Contrasting this, Montana and Wyoming experienced much wetter than normal conditions. The high precipitation and warm temperatures in places like Montana and Wyoming have had interesting implications for snow, which we'll dive into later. Okay, now looking deeper into the data once again, we can see how these state level patterns represent a more detailed mosaic of dry and wet conditions. Here I'm showing the same data as before for precipitation, but not aggregated to the state level. Important to note is the touching corners of Kansas, Oklahoma, Arkansas, and Missouri. This region in general had its driest December on record, which strongly impacts the representative state level rankings, which we looked at before. Okay, on this slide, we're moving on to look at minimum temperature departures from normal on the left and maximum temperature departures from normal on the right over the last 30-day period. So now we're not just looking at December, we're looking at December 16th through January 14th. Temperatures from this window of time are compared to those observed between the last climate normal, which is between 1991 and 2020. Yellow and light green colors indicate near normal temperatures. Green, blue, and purple colors, which are generally not present, represent cooler than normal temperatures. And orange to red colors indicate warmer than normal temperatures. As you can see, minimum temperature anomalies over the last 30 days, as shown on the left, have been between 5 to a whopping 25 degrees Fahrenheit warmer than normal in the upper Missouri River Basin, including in places like Montana, Wyoming, and Colorado, as well as the western portions of the Dakotas and Nebraska. The remainder of the region is still much above normal, but generally more moderated compared to these other regions. Again, these temperatures have been particularly warm minimums have strong impacts on snow dynamics, which we'll look at later. Moving to the right, average maximum temperature anomalies exhibit similar patterns, though the most extreme maximum temperature anomalies have moved farther to the east, generally over Nebraska and the surrounding states. However, as you can see here, the entire Missouri River Basin and into the Ohio River Basin have been well above normal in terms of minimum and maximum temperatures. Let's quickly move on to precipitation over the last 30 days as a percentage of the average value. As an example of how to read this map, dark red areas represent 0 to 5% of average or almost no precipitation. Yellow and green areas represent approximately normal precipitation or 100% of normal. Dark green, blue to purple shading indicates upwards of 200 to 300 or 2 to 3 times the normal precipitation over this 30-day period. Precipitation patterns for this time period have been spatially variable, as you can see. In general, the northwestern portions of the domain, extending into eastern Montana, have generally been drier than normal. This dryness is also apparent in middle portions of the Missouri River Basin. But fortunately, some portions of the mid to lower basin received above normal precipitation, including locations like Iowa, Michigan, Wisconsin, which we'll see is also associated with snowpack dynamics. Next, we will take a look at how these recent weather patterns have impacted these snow conditions more explicitly. Here I'm showing the total snow water equivalent, or SWE, that is accumulated so far this season. So this represents the snow water equivalent on the ground. There may have been snow events that have occurred and then subsequently melted, which are not represented here. This is the snow that's on the ground. SWE represents the amount of water stored in the snowpack and is a useful indicator of potential runoff later in the year. I'm using two different data sets here. Observed snow water equivalent, or SWE, from SNOTEL stations, observed stations on the left, and modeled snow water equivalent from the SNODAS data set on the right. Starting in the northern Rockies and on the left-hand side, SNOTEL data shows how much of the mountainous terrain in Montana is currently near normal for SWE. However, the SNODAS product in the same area reveals that mid to low elevation snowpack across Montana is substantially below normal. This highlights an important elevation-dependent signal that station-based observations alone don't fully capture. Moving south into Wyoming, both data sets tell a consistent story. Higher elevations are generally at or above normal SWE, while, mid-elevation areas are generally well below normal. This agreement between data sets increases confidence that Wyoming's snowpack is strong in the mountains, but more limited outside of them. Now, moving into Colorado, both SNOTEL and SNODAS agree that a pronounced snow drought is present across the state, affecting both high and low elevations. This indicates limited snow water storage across Colorado heading into the core winter season. Discussion with our colleagues and friends in Colorado have exemplified concerns in this area. Snow deficits in December can be overcome throughout the rest of the season in general, but it becomes increasingly concerning to see these deficits persist through January. Without a large change in pattern, these conditions should be expected to worsen. Looking farther east using SNODAS, again on the right, a minor snow drought is also emerging across parts of Dakotas, particularly where snowfall has been limited so far this season, or like I said, it has fallen and then subsequently melted. In contrast, a clear snow surplus is evident near the Great Lakes, where persistent lake effect snow has produced well above normal snow accumulation. I'll come back to this snowpack story a little bit later in the presentation, but for now, the takeaway is that there's a strong elevation gradient across the West when it comes to snow, which will have interesting implications for runoff if they persist in over the next several months. I should note, though, that we are still early in the snow accumulation season, so there's still plenty of times for things to change. But how much snow are we actually missing or in surplus? Here I'm showing the snow water equivalent difference from average using the SNODAS dataset once again. Blue-green colors represent more than average snow water, while brown indicates less than normal snow water. As you can see, northern Michigan has a surplus of up to about 4 inches of water in some places. Contrasting that, there's a strong deficit of about the same amount, 2.2 to 4 inches of water or so across the mountains of Colorado. Looking farther to the north, we can see that the mountains of northwest Montana, Wyoming, and others are also missing a substantial amount of snow water at low elevations, but a surplus at high elevations. Okay, now let's look at one more graphic that puts the current accumulation in the context of the entire accumulation season. Here are seasonal SWE accumulation time series from the Army Corps of Engineers for the Platte and Missouri River basins. Red lines represent average conditions, while the shaded blue region represents this year. As you can see, this year's accumulation has been very close to average according to this analysis in the Missouri River Basin, which is shown on the right, but generally lacking in the Platte River Basin, shown on the left. However, like I said, we are still only about a third of the way through the accumulation season, as you can see in these time series, so there's still plenty of time to make up lost ground. Pivoting now to a different component of the cryosphere, ice cover over the Great Lakes. Here I'm showing a few graphics. On the left is a map of the current ice cover across the lakes. Gray shading shows current coverage, while colors represent surface water temperature. On the bottom right, I'm showing a time series of percent ice cover over the Great Lakes. The red line is average, while the light blue lines represent each individual year in the period of record, which started back in 1973. The black line is this year. As you can see in both the map and the graph, the ice accumulation season is off to a slow start at only 5.9% cover over the Great Lakes. But it is important to note that there's a lot of variability in the lake ice record, as you can see by all the small blue lines, and that things can change quickly. As a note, open lakes mean the potential for lake effect snow is possible, which we've already seen evidence for in Michigan. And again, all of this can be viewed through the lens of satellite imagery, which we can see from the VIIRS satellite in the upper right-hand side that shows all of the open water across some of the Great Lakes. All right, now moving on to soil moisture conditions. Here I'm showing soil moisture percentiles estimated by the NLDOS2 suite of soil moisture models. Low soil moisture percentiles from 20 to 1% are indicated with that light orange to red shading. Surpluses of soil moisture with percentiles from 80 to 100% tiles are indicated by the light green or dark blue shading. Generally, you can see that the eastern portion of the domain is generally lacking soil moisture, which is where we're also seeing persistent drought conditions, while the west is generally more than normal or so. This pattern reflects recent precipitation and snowpack conditions with wetter soils in the west, where snow and precipitation has been more persistent, and drier soils in the east, where deficits have been accumulated. Looking now at current streamflow conditions, here's a map of USGS stream gauges and flow rankings across the U.S. for the last 28 days. Across the gauge network, blue symbols represent above average flows, green symbols represent average flows, and orange to red symbols represent well below average flows. As a note, stream gauges this time of year can be frozen, which explains a lot of the missing data in the northern portions of the region. Despite this limitation, a clear pattern is still evident. Across the lower and middle portions of the central region, stream flows are generally below normal, reflecting recent precipitation deficits, depleted moisture, and long-term dryness. In contrast, portions of the western and mountainous regions show more near normal and above normal flows, consistent with recent moisture that has fallen in the form of rain at those mid to low elevations instead of snow due to warm atmospheric river-based moisture and warm air temperatures, causing some significant flooding in portions of western Montana. This was a real big impact in my region, but isn't part really of the central region, so I'll skip it for now. Let's take now a quick look at current reservoir conditions along the Missouri River Basin. This graph shows the combined storage capacity for the Fort Peck, Garrison, and Owyhee River reservoirs in millions of acre feet. The dashed brown line shows system storage in 2025, and the red line is this year. The dashed blue line represents the average storage of the system. Currently, system storage is below average for this time of year and lower than this time last year. For 2026, the U.S. Army Corps of Engineers is forecasting runoff in the Missouri River Basin above Sioux City, Iowa, to be near average at roughly 24.5 million acre feet, or 96% of average. However, the forecast indicates a delay in the delivery of water, likely due to the lack of low and mid elevation snowpack at this time. Higher elevation snowpack takes longer to melt, as you need warmer temperatures at higher elevation. Regardless, the forecast is suggesting improved runoff conditions compared to last year, albeit perhaps a delay. Let's conclude the current conditions portion of the presentation with a look at today's drought monitor, which was released today from the National Drought Mitigation Center. Across much of Nebraska, Kansas, Iowa, Missouri, and southern Minnesota, abnormally dry conditions remain widespread, with pockets of moderate drought persisting. In Nebraska, conditions have deteriorated over the last several weeks, enforcing drought in the middle portions of the Missouri River Basin. Recent rainfall has led to some localized improvements, particularly across eastern Kansas, southeast Nebraska, and southern Iowa, Wisconsin, and Michigan, where moderate drought has been reduced or even removed. In contrast, drought conditions have expanded across parts of eastern Wyoming, northeast Colorado, west central South Dakota, southern Missouri, Arkansas, and Texas, where precipitation deficits and elevated evaporative demand continue to dominate. Overall, this pattern reflects a central region where short-term rainfall has provided some relief in some areas, but longer-term drought conditions continue to shape impacts across much of the plains and the Midwest. But what recent trends have we seen in the USDM? Here I'm showing you the 10-week and 52-week change map of drought classes. So green colors represent improvements to the U.S. Drought Monitor drought classifications, while yellows and browns represent degradations. In response to the very dry and warm conditions across the plains recently, there's been a significant drought degradation across Nebraska, Colorado, southeast Wyoming over the last 10 weeks, which you can see on the left. Elsewhere, minor improvements have occurred, but generally it is more constrained across the region. Over the last year, we've seen some significant improvements across the upper Missouri River Basin, especially in places like Colorado and Montana. While Colorado and Southeast have experienced significant degradations, not improvements, as you can see.
Say, Zach,
Yes,
can I just butt in like I do
please.
and mention that portions of Illinois, Indiana, Northwest Ohio have seen sort of chronic drought conditions for quite some time. And
Yes.
even over the last 5 years, some places have a deficit of over 20 inches in some spots. And that shows up sometimes in streamflow because that's a little slower to react. And I guess I don't want to belabor this point, but the fact that drought's gotten so much worse in the Midwest, in, if you will, corn country, that it's something we're watching.
Yeah, absolutely. And something like you said that's been playing out over the last several years. Some of these deficits have been over 4 to 5 years that are really depleting groundwater, soil moisture, and stream flow dynamics. So thank you for that, Doug. I appreciate that. Now I want to shift gears and highlight some of the impacts that have occurred over the last few weeks, starting with a significant wind event that affected much of the Rocky Mountain region and even farther east from about December 17th through the 18th and longer into December farther into the east. So, this was an unusually intense and widespread windstorm that occurred in Montana, or across the region. And in Montana, one of our mesonet stations in Bynum West, which is in Teton County, recorded wind gusts of up to 104 miles per hour on December 17th. Rapid City, South Dakota reported record gusts of around 94 miles per hour the following day. However, this event was very widespread across the West and ultimately farther into the east, like I said. The strength and extent of this event led our governor, Gianforte, to issue an executive order declaring a wind disaster across the state of Montana. At the height of its storm, more than 31,000 customers across northwest Montana were without power, and numerous communities experienced blocked roads, downed power lines, damaged trees, vehicles, and structures. You can see some of this damage presented in some of these articles that I'm presenting here. From a meteorological perspective, this event was driven by a rapid cyclogenesis of a mid-latitude cyclone crossing the Rockies, which produced extreme pressure gradients and sustained high winds. And in some cases, kind of where I am, topography fueled the wind, funneled the wind to make things particularly even more intense. Conditions were severe enough to prompt a first of its kind, particularly dangerous situation wind warning in Colorado. So, again, that's the first time in Colorado state history that that has occurred. And while windstorms are not uncommon in this region, the magnitude and duration of this event was exceptional and caused significant impacts. All right, now I want to pause and take a closer look at what I mean by an unconventional snowpack, because I think this figure really helps to illustrate what's going on. On the right, I'm showing snowwater equivalent in the Sun River Basin in Montana, which is a tributary to the Missouri River. The plot shows snowwater equivalent, again, SWE, on the x-axis, distributed by elevation on the y-axis, represented as a volume in anchor feet. The blue shading represents current conditions for this year, while the gray shading shows the historical median across the period of record, which is relatively short for this model to note. What stands out immediately is that the highest elevations, where most snowtel stations are generally located, snowpack is near normal. However, as you move down slope into the mid-elevation terrain, snow water equivalent drops off sharply, as you can see by the difference between that blue and gray shading. This means that we can have what looks like a quote unquote average snowpack in the mountains, while much of the landscape below is missing snow. And while these low to mid elevations might have a lesser depth of snow, maybe only 6 inches or 12 inches, because it's so much, there's so much area distributed at those lower elevations, it can result in large deficits of volume of water, which is what you're seeing here. So what this means is that the snow accumulation this season so far has been highly elevation dependent. And second, warm temperatures have raised the rain-snow transition, and persistent warmth has pushed this elevation at which precipitation falls at higher elevation as snow to higher elevations than normal, limiting that snow accumulation outside of the highest terrain. So this is what we're seeing, a lot of rain that's occurring at these mid to low elevations. As a result, the mountain snows retained snow while lower elevations did not. So there may have been precipitation, but it either fell in the form of rain or was in the form of snow that ultimately melted. Precipitation that might normally contribute to snowpack at these elevations instead fell as rain. And finally, this snowpack structure really does matter. Where snow is stored across the landscape influences things like runoff timing, soil moisture recharge, and water supply, which we kind of saw in some of those timing graphics from and forecasts from the Army Corps of Engineers. A snowpack concentrated only at the highest elevations can lead to a delayed or more compressed runoff with greater sensitivity to spring temperatures and storms. So the unconventional snowpack we've been discussing is already translating into real-world impacts across the West and other places, which will cause subsequent impacts downstream as well across the basin. One of the most immediate impacts that we've seen has been on winter recreation. Warm temperatures and low snowpack at low to mid elevations or cross elevations in Colorado have forced many ski resorts to delay openings, limit terrain, or rely heavily on things like artificial snowmaking, increasing costs and water demand. Beyond recreation, snow drought is raising concerns about water supply later in the year. With less snow stored naturally across the landscape, particularly at those low elevations, there's increased uncertainty around runoff timing and summer water availability, especially in these snowmelt dominated basins like the Missouri River Basin. In some regions, precipitation falling as rain instead of snow has also increased short-term risks, including runoff inefficiency and unlocalized flooding, where failing to provide long-term water storage. This is what we've seen a lot of in Montana this year, really high flows for the season in December, which is unusual. Taken together, these impacts highlight how snow drought affects far more than just snow totals. It influences things like water planning, ecosystem health, energy production, recreation, community resilience, etc., across the region. All right, now I'm going to transition to the outlook portion of this talk and discuss what conditions are expected over the next week to several months. Here, I'm starting with the National Weather Service's 7-day quantitative precipitation forecast for the United States. Colors represent the depth of expected precipitation in inches totaled over the entire 7-day period. So the expected values in our region range from about a tenth of an inch in light green to upwards of 1 inch in blue around the Great Lakes. Unfortunately, the short-term precipitation forecast suggests that there may be no new precipitation in much of the western portions of the central region, as a really strong high-pressure system is dominating our weather patterns out here. Unfortunately, nor does it favor significant moisture for places like the upper Midwest or locations that have been kind of having these persistent drought deficits, like Doug was suggesting. Yeah, Doug? Oh, however, portions of Minnesota and Wisconsin are maybe looking like they're going to receive a bit more moisture, which is hopefully going to result in some more snowpack in these areas. Okay, quickly now, I want to take a look at near-term temperature and precipitation outlooks. Here is the Climate Prediction Center's 6 to 10-day outlook for temperature on the left and precipitation on the right. As you can see, there's relatively high confidence that a strong cold air event will occur across the Great Lakes region. Please check with your National Weather Service office for more details on this event, but some of the far kind of simulations in some of our climate models and weather models are suggesting that this could be a pretty substantial cold event. Other than that, the rest of the domain is generally expected to lean cooler than normal or have relatively near normal conditions for this time of year. As for precipitation, the outlook is leaning above normal in the upper basin, as you can see on the right, as well in some locations farther to the east, which maybe provide some much needed moisture for these regions. Okay, moving on now. Here's the Climate Prediction Center's 8 to 14-day outlook. So just a little bit farther into the future for temperature on the left and precipitation on the right. The temperature outlook is generally similar to the 6 to 10-day outlook, with cooler conditions expected around the Great Lakes and above normal precipitation in the upper basin, as well as further to the east. In this outlook, however, nearly the whole region is leaning above normal, which is welcome news in locations with longstanding precipitation deficits. So we can hope for more precipitation across the region. Okay, now moving on to the 1 month outlook, which is focused on February. On the left, I'm showing temperature outlook again, and on the right, precipitation. And these figures follow the same color scaling as the previous figures. Starting on the left, the majority of the upper Missouri River Basin is leaning cooler than normal. As we move farther to the south, we see that there is generally equal chances of above or below normal conditions. Moving to precipitation on the right, here we see that the outlook suggests that it is likely we will experience above normal precipitation in the upper basin around the Missouri River Basin in Montana and Wyoming, as well as above normal around the Great Lakes. there are generally equal chances elsewhere across the region. And this really is showing a kind of weak La Nina signature the CPC is using to create these forecasts, which we'll be looking at here shortly. But before we do that, let's look at the 3-month outlook, which is focused on February, March, and April. Again, these graphics show the same color scaling as before. As you can see in the figure on the left, the majority of the central region has equal chances of above or below normal temperatures, with a slight favoring for below normal temperatures in the north and northwest. Similarly, there's generally equal chances of above or below normal precipitation, although the outlook is leaning wetter than normal in the northern reaches of the Missouri River Basin. Again, similar again to that La Nina signature that we would expect to see. There is greater confidence of wetter than normal conditions around Indiana and western Montana. So what's driving this? Well, looking past the 3-month outlook, it is important to understand kind of the El Nino Southern Oscillation, or ENSO, and changes in the Pacific Ocean sea surface temperatures. These can impact regional air circulation patterns and, in turn, air temperatures and precipitation. Here I've shown the January ENSO forecast within the left-hand figure. Blue bars on the left-hand side of the graph indicate that a weak La Nina is still here, and that's what's driving those CPC outlooks so far, of that wetter and cooler in the kind of upper portions of the Missouri River Basin and around the Great Lakes. However, as you can see, gray bars indicate an increasing likelihood of neutral conditions dominating going into the spring. And you can see that going out even further, that there is some potential indication that El Nino could come, but that's pretty far in the future and uncertain. So really what we're looking at is that transition to neutral conditions in the coming months. So what drives that ENSO phase? To the right, I'm showing the current sea surface anomalies off the equatorial Pacific, which determine ENSO phase. As you can see, temperatures are below normal, as shown by that blue coloration, along the equatorial line in that region that I've highlighted with the red box, which is indicative of that La Nina condition. Although, like I said, we should expect these anomalies to subdue to neutral conditions or normal sea surface temperature conditions in the coming months. All right, moving on now, let's discuss the seasonal drought outlooks. Browns indicate an expectation of persistent or worsening drought conditions, while greens represent an expectation of improving drought conditions. As you can see, the drought outlook suggests a split of conditions. Drought is expected to remain across the western half of the Missouri River Basin, especially in Colorado. However, drought is expected to improve in the northern reaches of the basin around Illinois. I believe that this will depend strongly on how current snow drought conditions kind of worsen or improve, and how these precipitation forecasts really play out over the next couple months. So be sure to come back next month to see how conditions have changed. Finally, let's look at significant wildfire potential outlook. Now, this is something I usually wouldn't show in January, as it's usually a pretty boring map for this time of year for this region, but not this year. As you can see, there is above normal significant wildfire potential in Colorado and Kansas. This is in response to the warm conditions, really significantly warm conditions, precipitation deficits, and emerging snow drought across the region. As I said before, it's still early, so things can change, but these outlooks are certainly notable for this time of year.
Yep. And can we go back
Yeah.
just to kind of wind this up a little bit on the wind and fire. So
Hmm.
this is also a very windy time of year, especially in the front range and high plains and all that business. And if there isn't a considerable snowpack or a snowpack at all, which there isn't, that whole area from where you see red all the way north of the Canada border is susceptible to wildfire, simply because of wind. And like today, or is it tomorrow, that the 50 or 60 mile an hour winds are predicted, and we have warnings and such all the way up and down. It doesn't take much. And again, snow, if without snow, the plains can burn pretty quickly. So I'm not
Yep.
saying that they will. I'm just saying that the potential there is there this time of year without snowpack.
Yes, absolutely. Thanks for that. All right. And just to finish things up and wrap up, I want to start by saying thank you again for listening today. I know this is a lot of information. And here's kind of a brief summary of what I'd like you to take home. Temperatures remain a dominant signal. In 2025 and the start of the 25-26 winter, we had exceptionally warm conditions with record warmth across many of the western portions of the domain, those western states and Great Plains, as well as continued above normal temperatures across the region. Some of those really minimum temperature anomalies were really striking, like we were saying, up to 25 degrees Fahrenheit over the last 30 days is exceptional and has that huge impact on snow dynamics. Similarly, precipitation has been very variable. The upper Missouri River Basin tended to have wetter conditions, but it was warm, so we're not seeing that, really above normal snowpack. While parts of Nebraska, Kansas, Missouri, Arkansas, and of course Oklahoma, which experienced record dry December, we see just kind of a very dry signal that has played out over the last month in that region. Snow conditions have been particularly kind of unconventional, is what I'd say, but snowpack is strongly elevation dependent this year, with near normal mountain snow in Montana and Wyoming, pronounced with snow drought in Colorado, and emerging deficits in the Dakotas, and notable surpluses around the Great Lakes, where we have a lot of that lake effect snow. Stream flow are generally below normal across the middle and lower Missouri River Basin into the Ohio area. And, there's still those frozen gauges up in Montana, but like Doug was really kind of highlighting, that reflects these longer term drought dynamics that have been kind of playing out in that region. And drought conditions show these mixed signals. We have short term improvements in places like the Midwest, but drought has worsened across places like Nebraska, eastern Wyoming, northeast Colorado, and Central Plains, with snow drought adding to that additional risk of impacts, secondary impacts from drought, things like wildfire, like we said. So looking ahead, short-term outlooks lean wet and cool across northern portions of the domain, with equal chances generally elsewhere. We have longer-term outlooks that are pretty similar. We have a weak La Niña that's in place currently, but is expected to transition to neutral by spring. And overall, we expect a mix of kind of drought improvements and degradations moving forward. So, with that, I'm happy to turn it back to Doug. We can open things up for questions and discussion, and I'd like to say thank you. And here is our contact information if you're interested in following up.
Oh, yep. Except I'm not at NOAA.gov. It's just Gmail.
Oh, yes. Yes, 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 yes.
Gmail.com. For Doug.
Gmail.com.
Yeah, I'm not at NOAA any longer. Uh, Thank you very much, Zach. That was you had too much to cover and too little time, but that's the way it usually goes on these things. We have a bunch of really good questions, so we'll get right to those. There were some folks who mentioned how quickly all their snow melted, but how substantial the snow was earlier in the season, especially across the Midwest, upper Midwest, actually into the mid-Midwest, I guess. But several January thaws or December and January thaws took care of that. And then we had rain on top of that in some locations as well, which caused quite a bit of runoff, and pretty muddy conditions for a lot of folks. And depending upon if the soil was frozen or not, some of that rain might have improved soil conditions, but usually there's enough frozen soils to just force it to run off like a parking lot, if you will. Okay, so there was a question about ice jams, and we didn't talk too much about that across the region when we were coming up with this. So I think at the moment there's not a short-term worry about that. However, as Zach was starting to show, and it's not, I mean, he was showing the climate prediction outlooks for the next week or two. There is an indication of some cold air hitting at least the Great Lakes. Some of the models we're looking at today, and this will probably be more refined later today, these maps, showing a little more penetration of that cold air down into the eastern U.S. In fact, looking at some of these maps out 10 days and such, it looks pretty darn cold. Now, it's going to be January, folks. So our coldest time of year for most of us is like the third, sometimes fourth week of January. That's typical. That's the coldest time of year. It's about a 1 month leg from the shortest day of the year. Um, so, so ice jams, um, ice jams also happen after the ice gets really thick after a very cold event. So usually, not always, but often we see them in February and March in terms of real big jams and real problems. That doesn't mean we can't have one in the short term. They do happen that way. But at the moment, there's not too many issues. I guess there's one not too long ago in the Cedar River, according to what one person mentioned. And then we're talking about why the soil moisture, insight into why the West has more soil moisture despite the hot or warmer than normal conditions, and in some cases drier conditions. And Zach, you want to talk any more about that? The fact that we had
Yeah.
rain as opposed to snow, and
Yeah, exactly. Yeah. I mean, there was actually like one region, I mean, the kind of Pacific Northwest moving into Western Montana, which I know is a bit outside of this domain, had these atmospheric rivers tracking across, which brought quite a bit of moisture, but very warm moisture. So places like in Northwest Montana, we had I think in Lincoln County, we had a 24-hour period where we had 4 inches of precipitation fall, which caused record flooding in some of the rivers around there, the Yak and others, which resulted in some soil moisture recharge. And normally we would expect that to come in as the form of snow, but it came in as the form of rain and in some cases snow, but temperatures were close to that 32-degree mark. So as things warmed, there was infiltration into the soil. We don't really have many frozen soils in a lot of these areas because it's been so warm. So instead of what we would expect, where that snow would fall on the surface and kind of get locked up, and any of the moisture that was in the soil would be frozen. Right now, that isn't the case. So we're getting kind of infiltration into some of these areas where we would kind of generally expect it to be retained as snowpack. So despite it being warm, we have had wet conditions, which is what I showed here. Over December. And so in these places where it's been warm and wet, that's a recipe for, soil moisture recharge this time of year. So that's kind of one component of the story. And then like we were talking about, what's going on down in more of the central and eastern portions of the region have longer term drought dynamics. It's also been warm. There's been big lack of precipitation, especially kind of in this area. So, that's led to declines in soil moisture, as we would expect them for this time of year. Is
yeah.
there anything else you want to add there, Doug?
No, I think this map pretty much tells what's been going on. The fact that it's been so warm and that we've had rain as opposed to snow, especially at mid and lower levels, one could say is indicative of the shape of things to come or more common things
Yes.
in the future. It's to many of us, it's not a huge surprise, I guess.
Yep.
It's interesting, but it's not overly surprising these days. All right.
Agreed.
This is another good one for you, Zach. What is the impact of sublimation when measuring and
Yeah.
calculating snowpack?
Right. Yes. So in our
First,
snowpack,
first, 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 describe what sublimation is to
yeah,
folks.
yeah, absolutely. So sublimation is a phase change. So that when you melt, right, you go from solid to liquid, and that's a phase change from solid to liquid. You can also have a phase change between solid to gas. So what's happening is snow will go directly into vapor. So you'll skip the melt phase and go directly from a piece of ice to a piece of water vapor that's in the atmosphere. And so that loss of moisture from the snowpack is called sublimation. And that basically results in a reduction in the amount of water that is in the snowpack, but doesn't interact with the hydrologic system,
Hmm.
at least the terrestrial hydrologic system.
Right.
So, of course, in these observations, like SNOTEL, which is we're showing here on the left, that process is baked into those observations because it is literally what we call a snow pillow. We have a pressure sensor out on the ground, out on the landscape. NRCS puts these out. And as there is sublimation that's occurring, there is a reduction in the weight of the snowpack. So sublimation is captured in this. Also with SNODAS, SNODAS is a physical cryospheric snow model, and it does have a module that explicitly simulates sublimation. So SNODAS also attempts and does simulate that process. So, in some places where, like you were saying in the Midwest, where you had snow and then it was lost, and, where there's not this increase in soil moisture, that might be component of that might be sublimation. So it's certainly it's certainly a strong process. It's something that we experience quite a bit out in Montana because we have such dry air that you can have 2 feet of snow on the ground. And where we have some of our study sites with soil moisture probes, that snow will be gone by the time we get to April, and you will see no increase in soil moisture. So sublimation can completely chew away an entire snowpack, and there won't be any kind of positive contribution to the subsurface storage. So it's certainly an important piece. And like we were talking about, wind is something that increases sublimation. It increases basically the transfer of latent heat. So it's able, when we have windier, warmer conditions in the winter, we would expect to have a larger component of the snowpack lost to sublimation. So it's
Yeah.
certainly a part of this story for sure.
And Dennis, this is more on your angle. Any comments on frost depth? I know that some places were shallower than normal, especially those places that had snow on them earlier in the season, especially in the Midwest, I should say. Pretty, yeah. And then probably places in the West, as Zach was saying, no frost depth because it's been so warm. Anything you
Yeah,
want?
I posted in the chat the link to the frost depth map from the National Weather Service. The relatively warm temperatures and then the recent rains. Rain will also help thaw the ground, have limited the frost depths decently. There are a few places up to 20 inches, which is okay, but nothing astounding for this time of year.
Right.
We expect with the cold later in the month that they will go deeper. But if we're concerned about very deep frost depth penetration, that seems unlikely with some moisture soils and the relatively warm conditions so far.
Yeah. Yeah. Okay. I think that is all the questions that we've had. Yes, we had a huge wind event. We're going to have another one over the next 24, 48 hours across the high plains. As you can see, if you go to weather.gov, weather.gov, you can see the warnings and such out there. It's going to be quite an event, 55, 60 mile an hour winds, but nothing like the 80 to 100 mile an hour winds that we saw in mid-December across the whole Front Range. So anything else you want to say about the wind event? Yes, there were shutoffs. Someone mentioned that they had power shutoffs in Colorado because they knew it was going to blow, and any kind of electrical system or electrical wire that blows down could easily start a fire, and it would be devastating. Anything else you want to add to that, Zach?
No, I mean, it was just extreme.
Yeah.
104 miles per hour is pretty intense. I mean, enough
Yeah.
to push over cars and everything. So,
Right.
it was extreme, but I think it was mainly just the Colorado, one of our colleagues in Colorado, Peter Goebel, highlighted that this particularly dangerous situation for Colorado for high fire danger associated with that wind event was, the first in the state's history. So that's and it happened in December,
Right.
which is
Yeah.
notable.
Yep. All right. Well, hey, thanks one more time, Zach, for this. Really much appreciate that, and to you, Dennis, for being on, and the National Drought Mitigation Center, as well as Tanya, who hosted us today. So thanks, everyone, and we'll see you back in February, we hope, 19th. So have a great month, and don't get too cold later this month. It's going to be chilly.
Thank you.